So today we're going to be talking about how to design a geospatial data aggregation platform. So essentially what that means is we have a whole bunch of different data sources that are stored on various locations and are in a variety of formats. So for example, vector data, raster data, or even tabular data. And we have a user that wants to be able to access all of that data on some web dashboard that they can view and easily access. So the system that we want to build is something that's going to allow our user to access these types of data in a consistent format and in a way that's easily accessible and fast. So before we dive into the actual design of the system, let's first take a look at some requirements. So in terms of functional requirements, we're going to have some data that we want to pull from various external services. These external services are going to store all the data that we're going to be manipulating, and we want our system to support a wide variety of these services. Once we have that data downloaded, we're also going to want to be able to aggregate and normalize data across multiple different data sources. So we might have two different data sets from two different providers that we want to sort of join together and generate aggregate insights on. We also want our data analysis to update as the source data changes. So for example, if the source data set updates once every day, we should rerun our entire data process once every day to make sure that we always have the most up-to-date version of the data. And finally, we want to have some web dashboard that we can use to view our data that's actually accessible to our end users. For non-functional requirements, we really want to make sure that the loading of data in our web dashboard is very fast. We're going to be dealing with very large quantities of data, and we want to make sure that we can access the relevant details very quickly. We also want to make sure that we're able to handle multiple formats of data. So that could mean raster data, where we have a point for every latitude and longitude on the globe, or vector data, where our data consists of polygons and points spread across the world. We also want to make sure that we're able to handle extremely large data sets. So if we have a very high resolution data set that includes data for the entire globe, this could easily be hundreds of gigabytes or even terabytes in size for a single data set. So we want to make sure that we're able to handle that amount of data, even though our server might not have that much memory available. And finally, we want to have a reusable data API that we can use for any product, including the web dashboard that we're going to be talking about. So the first problem that we're going to tackle here is the data processing side. So let's take a look at a bare-bones solution that will accomplish this goal. The simplest way to do our data processing is to simply have a batch job running on a single server that'll go out to all of our data sources, download them, do whatever processing we need to do, and then upload them to some sort of data lake where they can be stored. Oftentimes, these types of data processing workloads will be written in Python and would use libraries such as Xarray or Pandas to manipulate these data sets, normalize them, and come up with a consistent format. A really good format to use for this type of data is ZAR. ZAR is optimized for cloud storage and is really good at holding large amounts of geospatial data while allowing you to download certain chunks of that data efficiently without having to download the entire data set. All this processed data can then be stored on a data lake, which would be something like Amazon's S3 or any other simple blob storage system. Now, this would work great for smaller data sets. However, we'll quickly reach limits with the memory available to this single worker node. If we have a 500 gigabyte data set that we're downloading from one of our sources, that data set probably isn't going to be able to fit into the memory of our single server, so we need some way to distribute that workload across multiple machines. To do this, we can utilize solutions like Spark or Dask, which are designed for distributing data workloads across multiple machines. So we still have our batch job here, but instead of running our data processing directly on that node, we're actually going to have our batch job send this workload off to some Spark or Dask cluster, and that cluster will consist of several nodes, each of which is responsible for downloading a specific piece of a certain data set, doing whatever processing it needs to do, and then uploading it to the data lake. Formats like ZAR are really effective in this case because they allow us to efficiently store pieces of the data without having to access the entire data set. If you're curious to learn more about how these distributed data processing frameworks work, you should check out our full video on the topic on interviewpen.com. Now, there's one more problem that we have here, and that's the batch job itself. We might have different data sets that need to be fetched and processed at different intervals, and we also might have dependencies between different tasks that we want to run, and that's quickly going to become difficult to manage with a single node here. A much better solution here would be to use a dedicated workflow orchestration tool such as Apache Airflow. So when we're using Airflow, we can create a DAG, or directed acyclic graph, of all of the tasks that we need to run in a particular workflow. So any of these tasks could be a Spark or Dask job that we want to run, which does some piece of this data transformation and processing pipeline. Apache Airflow will automatically handle parallelizing different pieces of this workflow that can be parallelized, and it'll also handle spinning up a worker node to actually run these different tasks. This worker node would then be the piece that's responsible for actually scheduling all of the tasks onto our Spark or Dask cluster to actually do the data processing. Introducing this piece here is going to make this whole system a lot more scalable and easy to manage, and it'll introduce a lot of observability to make sure that we understand what is running, when, and whether it has succeeded or failed. Now, the final piece of the puzzle here is our data API that we'll use to actually access the data that we now have stored on our data lake. Since we already have this data stored in a nice format that's easy to query, we could just have a simple API that can query the data in our data lake, and then our dashboard can utilize that API to access the data that we want our users to view. However, our data lake is inherently a disk-based solution, right? These are systems that are designed for large-scale analytics where we can't feasibly store all of the data in memory. However, for this particular system, we might have certain query patterns where we can effectively cache certain data in memory. With traditional types of data, we'd simply use a database such as PostgreSQL or MongoDB to store this type of transactional data, but there isn't really an equivalent to that type of system for the raster-based geospatial data that we're dealing with in this type of system. So in order to enable our clients to access data faster, we're going to introduce our own in-memory cache, which can store some of the data that's stored on this data lake. Our API will then be responsible for checking the cache before every read request, and then falling back to the data lake if the data isn't cached in memory. The API would also be responsible for making sure the cache is up to date and is taking advantage of the memory that it has available to it. Because this cache will store data in memory, this will be a lot faster than having to read from our disk-based data lake. So that concludes our sort of high-level overview of this type of system. We went through a lot of moving parts here, and if we go deeper into the weeds, into all the different pieces of this system, there's certainly a lot more things to consider than just which systems we're going to use. But this high-level overview of this type of system should give you a sort of idea of the types of services that we're going to utilize in systems like this, and should give you a good starting point to research more about this topic if you're curious. If you enjoyed this video, you can find more content like this on interviewpen.com. We have tons of more in-depth system design and data structures and algorithms content for any skill level, along with a full coding environment and an AI teaching assistant. You can also join our Discord, where we're always available to answer any questions you might have. If you or a friend wants to master the fundamentals of software engineering, check us out at interviewpen.com.